Okay, now I would like to explain about the vector magnetic potential due to current carrying conductors and inductance. So first the vector magnetic potential due to differential current elements. So consider a differential current element dl bar carrying current I, then according to Biot-Savart's law, the vector magnetic potential A bar at a distance of r from the differential current element is given by A bar equals to closed line integral mu naught into I into dl bar by 4 pi r into 4 pi r Webers per meters. Okay, this is the vector magnetic potential due to line current element. Okay, next one, due to differential surface conductor, the vector magnetic potential expression. Okay, just to replace I into dl bar by k bar into ds bar. Here k bar is current density and ds bar is differential surface area. Okay, next similarly, differential volume current carrying conductor vector magnetic potential expression. So closed volume integral j bar into mu naught into j bar dv by 4 pi r Webers per meters. So here j bar is volume current density and dv is differential volume. So these are the vector magnetic potential expressions with respect to differential current elements. So first one, differential line current carrying conductor. Second one, differential surface current carrying conductor. Third one, differential volume current carrying conductor. Here I current value, dl bar differential length. So k bar current density, ds bar differential surface area, j bar volume current density and dv differential volume current carrying, differential volume of the current carrying conductor. Okay, we know that the vector magnetic potential means the magnetic potential produced by the current carrying conductor. In vector magnetic potential case, current density j bar value not equals to 0. Okay, next one, the vector magnetic potential due to infinite length current carrying conductor. So consider an infinite length current carrying conductor along the z-axis. Okay, this is current carrying conductor, length equals to infinity. It lies along the z-axis from minus infinity to plus infinity, and current flowing through this conductor equals to I. So we know that the magnetic field intensity due to straight conductor h bar equals to I by 2 pi r into a pi bar. Okay, this is the formula already we derived. B bar is magnetic flux density, the relation between B bar and H bar. B bar equals to mu into H bar, so B bar equals to mu I by 2 pi r into a pi bar. So according to cylindrical coordinate, okay, assuming type of coordinate system, cylindrical coordinate system, and the relation between the flux density and vector magnetic potential, B bar equals to del bar cross A bar. B bar equals to mu naught into I by 2 pi r into a pi bar, and del bar in cylindrical coordinate system, dou by dou r into AR bar plus 1 by r into dou by dou pi into a pi bar plus dou by dou z into az bar. Okay, cylindrical coordinate system, del operator. So next here a bar equals to AR into AR bar plus a pi into a pi bar plus az into az bar. So next find del bar cross a bar. So in these two cases, okay, the unit vectors are AR bar, a pi bar, az bar, and del bar operator, AR bar component value dou by dou r, a pi bar component value 1 by r dou by dou pi, az bar component value dou by dou z. So similarly in a bar vector, the vector magnetic potential expression, so r component value AR bar, pi component value a pi bar, z component value az bar. So it equals to AR bar into KR bar into 1 by r dou by dou pi into az bar minus dou by dou z into a pi bar minus a pi bar into dou by dou r into az bar minus dou by dou z into AR bar plus az bar into dou by dou r bar into a pi bar minus 1 by r into dou by dou pi into AR bar. So next, by equating a pi bar terms on both sides, okay, here a pi bar term is there, by equating a pi bar terms we get mu I by 2 pi r equals to, here a pi bar term, okay, minus is there, so multiplying with minus we get it equals to dou by dou z into, okay, dou by dou z into AR minus dou by dou r into az. So here B bar is function of R, okay, B bar is function of R. So the A bar will also changes with respect to R only and will be constant with respect to Z. Your final answer is function of R. So A bar also function of R and it is constant with respect to z. So dou by dou z of AR value equals to 0. So constant with respect to z, so dou by dou z into AR equals to 0. So the expression becomes dou AZ by dou R equals to minus mu I by 2 pi R, or AZ equals to minus integral mu I by 2 pi R plus C, or AZ equals to minus mu naught into I by 2 pi. So integral 1 by R equals to ln of R plus C. So to find constant C value, so let AZ equals to 0 at R equals to R naught. Just assume AZ equals to 0 at R equals to R naught. So 0, substitute R equals to R naught, okay, we get C equals to mu naught into I by 2 pi ln R naught. Now by substituting this constant C in AZ expression, we get AZ equals to minus mu naught into I by 2 pi ln R plus mu naught into I by 2 pi ln R naught. So AZ equals to log of A minus B equals to log A by B. By using that formula we can write AZ equals to mu naught into I by 2 pi ln of R naught by R. So final expression A bar equals to, here A bar having only Z component value. So A bar equals to AZ into AZ bar. AZ equals to mu naught into I by 2 pi ln of R naught by R into AZ bar. Units are Webers per meters. Okay, this is vector magnetic potential expression due to infinite length current carrying conductor. Okay, next one, inductance. So a wire or conductor of certain length, when twisted into a coil, it becomes a basic inductor. Okay, a wire or conductor of certain length, when twisted into a coil, it becomes a basic inductor. For every conductor carrying current I and producing magnetic field with a flux density B bar, okay, there exists a self-inductance. When two such coils are placed very close to each other, there exists a mutual inductance between the two. If only one conductor is present, it having self-inductance. If two conductors are placed very close to each other, then there exists mutual inductance and also self-inductance. So first, self-inductance. So when a closed conducting path or a circuit carries a current I, a magnetic field of flux density B bar produced. This causes a magnetic flux pi, so which is given by pi equals to surface integral B bar dot ds bar. So the current carrying conductor produces the magnetic flux, and magnetic flux expression pi equals to surface integral B bar dot ds bar. Okay, we know that the inductance equals to formula flux linkages by current, and the flux linkages formula, so number of turns into flux. Okay, flux linkage is represented by psi equals to n into pi. So next, inductance equals to formula flux linkages by current. So for example, if only one circuit is there, so in that case the current flowing to the circuit equals to I. So the conductor produces the some magnetic flux pi. If a coil having n number of turns, the flux linkage is equals to n into pi, and the current flowing to the coil equals to I. In that case, the self-inductance L equals to n pi by I. N pi by I. The units of the inductance are henries. Okay, self-inductance is represented by L, mutual inductance is represented by M. So self-inductance and mutual inductance units are same, so units are henries. Okay, finally we know that a wire or conductor of certain length, when twisted into a coil, it becomes a basic inductor. If we connect electrical supply across the inductor, it stores the electrical energy in the form of magnetic fields, and that magnetic field of flux density equals to be the magnetic flux of inductor pi equals to surface integral B bar dot ds bar, and flux linkages I equals to n into pi, self-inductance L equals to flux linkages by current.